Okay, so let's continue to add a little bit more detail to how radiation and greenhouse gas effect are related to each other. So I mentioned the charges on molecules being spread like this, so we then end up with what is called a dipole moment or a neutral no net dipole moment. So in fact we are looking here at CO2, carbon in the middle, and it's symmetric with oxygen either side. So the bond dipole exists, but they are cancelling each other. So carbon dioxide in general has no net dipole moment, but it turns out that it has a bending moment which can still be excited by photons of energy in the long wavelength. What does that mean? We said the wavelengths of the solar energy are at shorter, we looked at the whole electromagnetic spectrum. Most of the energy coming in is at visible, so these wavelengths are allowed to go through these molecules like N2, which is 79% of the Earth's atmosphere, and oxygen, which is more than 20%. They are symmetric molecules and they allow short wave to go in and long wave to go back out, whereas a molecule like CO2, which allows short wave to go through, and even though it has no dipole moment, it is able to absorb outgoing long wave energy photon and create a bending moment. Why is that important? Because anytime you excite a molecule, it begins to vibrate, and the temperature, its kinetic energy, is a measure of temperature. So temperature changes, which is what is global warming, right? So here we have water molecule, which is the most famous one with the dipole. It's a bipolar molecule, if you will. Dipolar. So it has this angle of 105 degrees. Here is oxygen, here is hydrogen. They share electrons with a covalent bond, and because of this configuration you end up with positive charge here and negative charge here, so you end up with a bond dipole that doesn't cancel, so you end up with net dipole moment. As we said, this allows it to interact with electromagnetic radiation. So obviously water molecule is also a very strong greenhouse gas because it also reacts with the outgoing long wave energy. That's the kind of the critical thing. So the main thing then we need to understand is how this whole thing works. There is the concept of blackbody radiation. Here we are again looking at the electromagnetic spectrum. So let me, before I go to blackbody radiation, let's look at the intensity of the energy and wavelengths. We have already said that shorter wavelengths energy intensity is high. Here we are in the visible range, and we are here in the longer wavelengths. What are these temperatures being shown here? This is called Planck's curve. So essentially the energy that is total energy that is emitted by a black body. A black body is something that absorbs energy at all wavelengths and emits at all wavelengths. Okay, so you can think of an iron ball. If it is not warm, it just looks dark, but if you put it in fire like a blacksmith does and keep heating, you can begin to feel the energy first at long wavelengths, low energies, so you can feel the heat but you cannot see any color. But if you keep heating it, it can get red and then white depending on what temperature it reaches. So that is the general idea of a black body. Then all the energy that is emitted by a black body at all wavelengths can be integrated, and it fits the curve like this, let's say at 6000 Kelvin, and the area under that curve will be equal to the total energy emitted by that black body. So sun is somewhere around 5250 degrees or so. So you can see how the wavelength here changes. So lambda max is the wavelength of the black body at that temperature. So sun is emitting to us at basically looks white during the day, right? During the evening and in the morning it can look different colors because it is traveling through different lengths of the atmosphere and so on and so forth. But essentially the maximum wavelength and the temperature, maximum temperature, can be related to a curve that explains the total energy emitted. So here you have total energy being lower at 5000 Kelvin maximum temperature, further lower at 4000, 3000, and the wavelength increases. So shorter the wavelength, higher the energy. So this maximum wavelength decreases down to here. So this blackbody radiation has this complicated relation with wavelength and temperature at which it is emitting. There is the Planck's constant, speed of light, wavelengths, and then this complicated relation. And we are looking here at energy coming from the sun, again ranging, spanning UV to visible to near IR, and here is Earth emitting infrared energy at much longer wavelengths, much lower energy. So the intensity of black body radiation in arbitrary units according to Planck's law as a function of its wavelength in nanometers in the top panel, this one, and micrometers here in the bottom panel. This is the bottom panel. The sun's temperature, sorry, I said 5200, it's about 6000 Kelvin with a peak in the visible part of the spectrum. So this is how we infer sun's temperature. There are many ways to measure it, but looking at its peak energy, you can fit a curve to it, and it tells you based on the wavelength where the maximum temperature is. Okay. With a peak in visible part of the spectrum. The blue curve in the top panel shows Wien's law, which describes how maximum moves towards larger wavelengths at colder temperatures. So this is the Wien's law here, the blue line. The bottom panel shows curves representative of sun's and Earth's temperatures. Note that the bottom panel uses a logarithmic x-axis here, and that the values of for the sun are about 6 orders of magnitude larger than for the Earth. So here is energy from the Earth, which is 6 orders of magnitude smaller than energy output from the sun. But the main thing to remember is that the energy curves, the Planck curve for the sun and the Earth, are completely separated with tiny bit of overlap at the wavelengths, which are too long for the sun and too short for the Earth. Okay, so it is better to understand the concept of temperature here then. Heat is energy, so that's the integrated amount of let's say temperature. For example, think of a bucket of water. You can measure its temperature, but the heat is the amount of energy it has. So the warmer it is, for example, higher the heat and longer it will take for it to cool if you just set it outside and let it lose the energy, right? What is being shown here is the temperature of an ideal gas, which is proportional to the average kinetic energy of the particle. So think of absorption of shortwave or long wave. We said it produces electronic states, first or second electronic states from the ground state. That is increasing its energy, and that is a measure of temperature. The size of helium atoms relative to their spacing is shown to scale here under 1950 atmosphere of pressure. So helium under very high pressure is shown here in this animation. The atoms have a certain average speed, slowed down here 2 million fold, 2 trillion fold from that at room temperature. So for the sake of this animation, the speed of the helium atoms has been slowed down. What are we trying to show? Basically, the higher the temperature, more rapidly these molecules will be bouncing around. So that's their kinetic energy. So when you put a temperature thermometer or some probe to measure the temperature, molecules are bombarding the instrument, and you have somehow calibrated to measure the average kinetic energy, which is the temperature. And there is details. For example, it is assumed that the fluid is isotropic, so that turbulence is uniform in every direction, so that whatever you measure is the average temperature of the system you are looking at. Okay, and so on. So these are basic concepts you probably have been exposed to, but it's good to look at it again. So let's quickly look at the spectral radiance again in watts per meter squared per nanometer of wavelength here in nanometers. So at the top of the atmosphere, the yellow line is basically like a blackbody radiation. So the nice Planck curve can be fit to it with 6,000 degree Fahrenheit degree Kelvin temperature we saw here. But what happens once you look at what is reaching the surface? So if you look at radiation at sea level in these red curves, then what comes through from the top of the atmosphere to the sea level depends on the gases that are in there and how much of the sun's energy photons they can absorb. So you can see the various gases here. Oxygen, ozone is absorbing in this range, obviously UV that we mentioned. Oxygen is somewhere here. Water has many bands of absorption of shortwave energy. So water is a greenhouse gas, so it can absorb long waves going out as well as short waves coming in. And this is H2O at many bands. CO2 is out here, and again H2O over there. So these are the main greenhouse gases. Ozone, oxygen has a sharp brand here, but as we said, it's not a greenhouse gas because it allows shortwave to come in, even though it's sensitive in to UV, as we said, and it allows long wave to go back out, whereas some gases allow shortwave to come in but absorb long wave. Some absorb only shortwave or reflect shortwave or scatter it and do not react to long wave, and so on. All these depend on their particular properties and so on. So the greenhouse effect is essentially what we are talking about here. We need to understand what exactly happens when sun's energy is reaching the top of the atmosphere, and what is reaching the surface is different. How different, and what exactly does it mean for the temperature of the surface, temperature of the atmosphere, and so on and so forth. That is the greenhouse effect. So we will see that any body, any molecule, atom that has any substance that has temperature tends to emit some radiation. So that depends on its emissivity, some Stefan Boltzmann constant, and then temperature to the fourth. Okay, so that is the flux of energy coming, let's say, from our body, from a pot you are heating, from any surface that is getting heated by sun's radiation, and so on and so forth. So we'll come back and add more details to this and look at energy balance. Okay. Just listen to this again and make sure you understand. It's very basic. Short wave coming in, long wave going out. We are going to look at how they are balanced and why they are different. So input, output, look at how delta X, delta T happens, where X is the temperature, and then everything else follows from that. Okay, so we'll just keep adding little details, but make sure you understand. Okay.